Let's record. All right, I'm going to share the screen. And let's go to here. All right, everyone see my screen?
Yes.
All right, so
Yes.
this lab is a lot of just comparing pitches. And basically what we want to be able to do is compare the moons in our solar system to our moon here on Earth, okay? So basically you're going to get a tour of the different moons around Jupiter and Saturn. Really, those are the two planets that they focus on. So what I got over here is just some pictures of our moon. All right. First one here, you can see we're looking at a lot of craters. And we could actually get a relative age of some of these craters just by observing what's going on. So, for example, if I look into this area right here, let's change the color. Right, where I'm making a little box in red, and I label these craters, you know, 1, crater 2, crater 3, crater 4, and we'll make that 5, right? Out of those 5 craters, which one has to be the oldest? And how do we know?
Crater 1.
Crater 1 has to be the oldest, and how do we know that?
I don't remember.
And in geology, we would call this superposition. The other 4 craters are sitting on top of it, right? So do you see how like crater 1's outline here is kind of missing? Right? That's because the other impacts happened after crater 1 formed. So crater 1 would be the oldest, and then we could come over here, you know, and I'm going to erase crater 3, but if we look at 2, 4, and 5, I'm going to interpret this as 2 being the second oldest because it sits on top of crater 1, 4 sits on top of crater 2, and 5 sits on top of crater 4, so 5 has to be the youngest, right? I mean, you could also think about it if I made pancakes this morning, right? And as you take the pancakes off the griddle, right, the oldest pancake when you make your stack is always on the what? As you layer them. The oldest is always on the
Bottom.
and the youngest has to be on the top. So we could take that kind of analogy and just apply it to the craters here, and we could get a relative age, right? Like, I can't tell you, you know, when crater 5 that impact actually occurred, but I could say, hey, you know, that impact that formed crater 5 happened after, right, crater 1 formed. Does that make sense? And just kind of based on how they're sitting there. Okay. Over here, picture 2, we're looking at ejector rays. So sometimes what happens is after the impact, all that debris that gets kicked up from the impact gets shot all around and like almost like a splatter all around here. And you get these rays that form around the craters. And then picture 4 here of our moon, and these are all diagrams of our moon, right? We're looking at the mares, which are basaltic lava flows. And any crater that was in that area, right, would have gotten covered. And these would be nice, smooth plains here that covered thousands or hundreds and thousands of miles. Not hundreds, 100,000 miles, but hundreds or thousands. All right. And you can see like down here, we have a lot of craters, right? And then we have our mares and basically nice, smooth, basaltic rock, right? So that's our moon, and that's what we're really going to compare the first few moons to. So the first thing you want to do here is our moon is figure 16-1. Okay, and they're going to go over the impact basins, the resurfacing, ejector rays, and whatnot. So 16-1, label this, make sure you know that this is our moon. Okay, and these are some of the features that are on our moon. Okay, the resurface areas are the mares. Okay, then we go to the data table here. All right, so basically they give us the planet. We have the moon for that planet. We have how far away, the distance the moon is from the planet. We have its radius, the size. Okay, we have its mass, and then we have the density right there. So we got our columns. And the only planet that has multiple moons listed is Saturn. So these moons here all belong to Saturn. Okay, and the first question is really just a analyzing the data table question here. And basically what you want to do is you want to see if there's a trend. Sorry about that. Between radius and mass with distance from Saturn for these 4 moons. Okay, so you should really start this answer as like this, as distance increases blank, comma, mass does what? As distance increases, the radius does what, right? And then your answer kind of goes behind that. Okay, and we're getting that by just analyzing the data here. Sorry, that happens once in a while. I moved the document. There we go. Okay, and we get that by analyzing this column here with these 2 columns in green here. Everyone see that? Okay. Next, we're looking at Jupiter's moon. Okay. I can't pronounce most of the names. My pronunciation stinks. We know that from class. So I just call them the planets' moons that they're on. But both of these figures are for Jupiter's main moon here. And we're going to compare it with Earth's moon on figure 16-1. Okay. So you just kind of got to go back and forth comparing from this page to this page. And we're looking for, surface features that are similar and how are they similar? Very, very simple questions there. Then we're going to go to the 4 Saturn moons. Now, Saturn has one move that is pretty amazing. And it's got a little video here. Let me know if the audio works on your end. If the audio doesn't work, I'll show you the news article here where it has the animation. Let me see if I can get this to play. So this is Enceladus.
This week, NASA held a live event.
Can you hear that?
Yeah.
Yeah.
To reveal its latest findings about Enceladus, one of Saturn's moons. Scientists announced that the Cassini space probe has detected hydrogen gas coming from cracks in the icy crust, indicating that the moon's subsurface oceans might be able to, dramatic pause, support life as we know it. Finding hydrogen is a big deal because it's a chemical we think is essential for life to form, the others being carbon, nitrogen, oxygen, phosphorus, and sulfur. We have now detected all of those on Enceladus except phosphorus and sulfur, but we suspect those elements are present in its rocky core as well. To detect the hydrogen, Cassini passed through a plume of mostly water vapor coming out of the cracks, or tiger stripes, in Enceladus's crust. Enceladus is too small to keep hydrogen in its atmosphere, so the hydrogen must have come from the ocean inside the crust. The plumes of vapor spring up above hotspots, indicating hydrothermal activity exists on Enceladus's seafloor. Again, this is kind of a big deal because of what we know about our own planet. Hydrothermal activity occurs on Earth when water vapor seeps into the seafloor and is heated by magma. The heated and mineral-rich water then bursts back through the seafloor, and amazingly, ecosystems tend to spring up around it. Instead of using the sun's light to sustain them, the organisms around the vents rely on heat and chemicals for their energy. NASA's scientists speculated that something similar could be going on around Enceladus's hydrothermal vents. Using a process called methanogenesis, potential life forms could combine the hydrogen we now know is on Enceladus with carbon dioxide to produce energy, with methane as a byproduct. Methanogenesis is at the root of our tree of life, and may have even been critical for life on Earth to start. One NASA scientist was quick to point out, though, that Enceladus might be too young to have given life enough time to form. It could be the conditions are right, but nobody's home yet. If there is life down there, Cassini won't be going to find out, partly because it was never equipped to detect life in the first place. Frankly, NASA didn't expect to find so many indicators that Enceladus could support it. The plan is to intentionally crush and vaporize Cassini using Saturn's atmosphere to ensure it doesn't crash into Enceladus or Titan and contaminate any life forms that might be living there. Cassini's grand finale is scheduled for September of this year, 1 month shy of 20 years in space. NASA's next mission to an ice world will be the Europa Clipper in the 2020s. The Clipper mission will study Jupiter's moon Europa, another ice world with plumes of vapor rising above it. At over 4 billion years old, Europa is much older than Enceladus, and some at NASA believe that extra time makes it a more likely candidate for supporting life. We're just going to have to go there to find out. So let's say we find life on one of these moons. Then what do you think happens next? Let us know in the comments, and don't forget to...
All right, we're gonna pause it there. I just want to make sure. Tasha, did you get in?
I'm on, Professor. Thank you.
Okay, you're the one who you just emailed me, right?
Yeah, I'm on.
Okay, I just want to make sure you're in. Okay,
Thank you.
no problem. Okay, so go back here. So Enceladus, right? Really interesting stuff going on there. They have underneath the surface oceans, and they believe that, you know, if there's going to be a chance of life in our solar system, it might be on the moon over here in going around Saturn. Okay, so basically in this part, step 3, you got your 4 moons, and again, it's just comparative. All these questions just have you compare their 4 moons. You know, when we're looking for resurfacing, what are we looking for? Nice what? Smooth plains, like on the Earth, on Earth's moon, like the Mares, okay? Saturation cratering, we're looking for what we saw on Earth's moon, okay? So again, all these questions, you're just looking at the pictures, and we're just doing a lot of comparing. Then we go to step 4. This is Saturn's moon and Neptune's moon, Titan and Triton, okay? And again, it's a lot of this is just comparing. Now, when we go to this figure here, 16.4, you got 2 pictures. You got A and B. Make sure you realize that picture A is Lake Mead. This is behind the Hoover Dam on the Colorado River, while picture 16B is on Titan. Okay, so this here is on Earth, and this picture here is Titan. Okay, and again, we're just comparing the pictures, characteristics, and observations that we can make. Okay, and then we go to Triton, and again, it's what region on the Earth's moon is similar, and it's just comparing. And you basically didn't just put it all together. And that's really the lab here. Again, it's a very simple lab. Oh, sorry, that's my little one. Just comparing pictures and whatnot. Let's see if I can figure out how to get to the Zoom. Any questions on it? Am I still on with you guys?
Yep.
Yes. Yep.
Yeah, because I lost you guys over here. I don't know how to go. There it is. Oh, no. There we go. Zoom. No.
Actually, question number 8, what does it mean, the particles of the E ring?
Give me 1 second. Screen sharing has stopped. Okay. So let me just get here. Let's say fine. So the E ring is they're talking about Saturn's E ring. So if you go question number 8, we got to backtrack, right? And basically this is talking about one of the rings of Saturn.
Thank you.
All right. Anything else from anyone, or?